Hi folks. So this is going to be an audio only video. I'm going to still be drawing on our canvas here, but I didn't feel like showing my face was really adding anything to this video. I want to pick up where we left off, which was this radial force that's needed to have an acceleration, a centripetal acceleration in our system. So for our radial forces, what we're basically saying is that the sum of our forces of forces in the radial direction, in the r direction, has to sum to MAC, right? That's probably a better way of saying that, is that the sum of the forces in the radial direction, so now we're talking about R as opposed to X or Y, as we've done before, is going to be equal to MAC, M, our centripetal acceleration then. I really want to be careful of talking about this in terms of centripetal acceleration and not a centripetal force. Right? There really is no such thing as a centripetal force, but there are forces, radial forces, that give way to a centripetal acceleration, cause a centripetal acceleration. So again, we don't really say that a centripetal force, we could just say forces that cause a centripetal acceleration. So we can also rewrite this as M, let's do this nice, mv squared over r, or another way of writing it, m omega squared times r. So these are perfectly fine, but they are now our rotational Newton's second law here. So when thinking of a rotating or turning object, anything that spins, we want to really kind of picture a camera almost floating just straight behind it. If we think about a nice circle here and a little, let's say a little go-kart that is going through and going at this tangential speed, let's call it v, and they are some r from the center of our circle here. We want to imagine just kind of following right in back of it as it goes along. And if we follow right in back of it as it goes along, all we see is this little go-kart here, wheel. And we just see it kind of moving along. We keep seeing it make a turn to the left, right? We're not seeing it actually turn to the left, but we keep, following right behind it. And the left-hand kind of side here for us, if I separate this just a little bit, the left-hand side is our radially inward side. Right? And if I think about the right-hand side, I'm radially outward, right? So again, I'm considering myself just constantly behind here, even if the go-kart ends up back over here, right, at some time, and it will, I'm right behind here. I'm right just considering a little camera, little GoPro or something that's hooked up to the back bumper, right? And so this is my almost static viewpoint, right? So now instead of left and right being positive or negative x, what we're kind of saying is that it's positive or negative r. And then in front of me or behind me, right, I'm then talking about the theta direction, or the direction that my tangential speed is going in. So no matter where this car is on this track, I constantly just see this picture of a radially inward and a radially outward if I'm looking from left to right. So thinking about this in a free body diagram kind of way, if I were to draw the forces on this little go-kart, remember, we always put just a dot as our body here. I would say, of course, the easy force is going to be gravity. I have some mg of my go-kart. And then I have the floor, which is applying some force up, our normal force. And then if I think about the motion of this thing, I need to have an acceleration radially inward. I need some centripetal acceleration, right? So I need a force then that is radial. And because I can't speak today, there we go. So something needs to be pulling me in, right? Something needs to be pulling me into the circle here. Let's think about this a slightly different way. All right, we're going to go back to our grand view and our go-karts over here now. All right, so we got our go-kart. We have these tangential velocities. If I don't have a centripetal acceleration going inward, another way of talking about that is that I'm increasing the radius of my circle, right? I'm basically falling out of my circle at that point, right? I'm getting a larger and larger R. I'm moving radially outward, right? And the car doesn't, the car kind of, quote unquote, wants, I'm going to put big actual quotes, to move out of the circle, right? But that's not actually what happens here, right? It would only happen if we were skidding on ice or something like that, a wet road. The car wants to move out of the circle just because of inertia. Really, it doesn't want to move into a bigger circle. It wants to go just in a straight line. But something keeps it in. Some force keeps it in, right? If I want to move out and something opposes that, I mean, that sounds suspiciously like friction. And it is. The friction between the tires and the ground here are actually keeping me in this circle. There is a static friction force keeping me in my circle. It opposes the outward possible motion by pointing inward. Right? So a car without friction would just continue on its path tangent to our circle here. That would be out of the circle, right? That would be radially outward. But friction keeps us radially inward, right? It gives us a force that that provides a centripetal acceleration inward. So without static friction, we actually can't go in circles like this in a car. Now that's different from the kinetic friction that might be happening in the direction of actual motion, right? In the direction this way. Our static friction only points inward. So there can be multiple kind of frictional forces working on an object, depending on which direction we're actually looking at here. So again, really haven't. So the Fn, the mg would actually be in the z direction, right? For this guy and that guy, and then I'm talking about the radial friction force as the radial direction, which means our theta direction. Right? Our theta direction actually pops in and out of our page here. And that's kind of hard to draw even with a bit of technology. That's just a little bit hard to draw right now. But our tangential acceleration, or our theta direction, right, also might have some forces on it, some frictional forces which move the card forward. Or even slow it down. So that is a quick video just talking about how friction keeps cars in a circle, and also just that a centripetal acceleration is needed to be caused by some net force in the radial direction. Right? The radial forces need to sum to give us our net acceleration, our centripetal acceleration here. We'll get some more practice drawing some free body diagrams that actually rotate. But the main idea that I really do want to point out and reiterate is that we are this little camera. We are this little camera following behind our car here, such that we can just kind of have this almost static view of the radially inward and the radially outward. So that's that for this video. Thank you very much, and please, as always, let me know if you have questions.